I know you all, and will a while uphold the unyoked humour of your idleness. Yet herein do I imitate the sun, who doth permit the base contagious clouds to smother up his beauty from the world. Hello, everybody. Yeah, we've been talking about crystals, right? There are ionic crystals, ammonium chloride. There are covalent crystals, something like solid carbon, right? Graphite. And then there are molecular crystals, like sugar, sucrose. So all these crystals have something in common. They're poor conductors of electricity. They're not bendable. They're granular, right? So they're all real brittle. Oh, get them all in here. And they don't conduct heat, right? You can't stretch these into wires. You can't bend them. So what crystals can you do that to? The answer is metals, metallic crystals. All right, so these are very different crystals, right? This is a solid, right? It's crystalline structure. You get these, face-centered, body-centered, rhombohedral. I don't know. I made that one up. Is it rhombohedral? I think it's rhombohedral. Crystal shapes throughout the lattice, but they're different, right? They're bendable, right? Malleable, right? So this is copper, bendable, zinc, bendable. And you can stretch them into wires, right? So malleability is bendability. Ductility is being able to be stretched into wires. And if I shove this thing in the electric socket, it'll conduct electricity. So why? Why are they ductile? Why are they malleable? Why do they conduct electricity? Well, the answer is because we have a different crystal type. Metallic crystals are held together by metallic bonds. So what the heck is a metallic bond? Metallic bonding. So, conduct electricity, malleable, ductile. Why these properties for metals? Well, all right, so as expected, right? So we're going to have metals packed together, right? And metal's going to be occupying the lattice points in our crystals. Body-centered, face-centered, whatever. Except that actually, at the lattice points, you don't have an atom. What you've got is a nuclei and the core electrons. With metals, right, as we know, right, metals give up electrons in chemical reactions. They don't hold on very strongly to their outer electrons. So what happens is those valence electrons aren't really owned by the individual atom. They're shared throughout the crystal. And this helps stabilize the crystal in such a way that you get these properties. So kind of the ultimate in delocalization, right? Those valence electrons are shared over, basically the entire crystal. So the operative words there are core electrons and nuclei at the lattice sites, and delocalized valence electrons holding the crystal together. And this is deep. This is as deep as we're going to get into it. I used to get into the whole molecular orbital representation of it. We're just going to talk about a sea of electrons. Right, so the visualization at the lattice points, you got the nuclei and the core electrons, and you got the valence electrons causing like this sea of electrons that enable electrons to be able to travel through it. Right, so there are conducting bands through metals. Right, so this is why it's this sea of electrons that allows the electrons to travel through the crystal. So with an aluminum atom, you've got the core electrons with 13 protons and 10 electrons, and those outer 3 electrons are shared with the rest of the group to form that sea of electrons. All right, so when I put a metal with a metal, I don't get a reaction, right? Metals, neither one is trying very hard to take the other one's electrons, so I don't get a transfer, I don't get bonding. But what I can do with metals is mix them. And when we mix metals together, we get alloys. So there's 2 kinds of alloys. There's substitutional alloys where you get atoms of about the same size, and literally you pluck atoms out of the host crystal, and you insert other metallic atoms in to get different properties. For example, brass. When you take the copper crystal and you take some of the coppers out and you mix in zinc, right? So it's 33.3% zinc. You get brass, right? So it's going to have a different. I'm not really sure what the benefit is of brass, right? But you got copper and you got zinc, and I guess they get harder. Do they get harder? I don't know. Bottom line is when you mix these together, you get an alloy, brass. Now, sterling silver, right? We've got silver, and what you want to mix in is a little bit of copper, and that helps the silver from being so reactive. All right, so the copper, I guess, allows the silver to stay longer. Actually, silver degrades pretty quickly, right? So, in the ocean, right? If you drop your silver coins or your gold coins, the gold coins will be there. The silver coins will oxidize, right, to some kind of silver ion, well, into silver ion. All right, so if I have copper, the copper crystal, and I slip in some zinc atoms, the important thing is they're about the same size. So if I insert some zincs into this crystal, I get an alloy. Now, whereas with interstitial alloys, right, you've got, again, you're packing these metal atoms together, and what you have is little spaces between the metals. And what you can do is take small atoms and insert them in between these pockets between the atoms and get what's called an interstitial alloy. The classic example of an interstitial alloy is steel. You want to make a sword out of iron, you're going to get a very bendable sword. So you want to stiffen up the iron so that it's you get a better sword. You put carbon in the holes. So you put a little bit of carbon in there, it's somewhat malleable, right? So it's not quite steel that can kind of bend. You put more carbon in, you get harder, and then you get tool-grade steel. Now, if you put too much carbon in, all of a sudden you lose that malleability of the iron, and you'll have a shovel that'll shatter like glass. So you don't want to put too much carbon in, but you want to put enough to stiffen up the iron. So again, what does this look like? You've got iron atoms, and in between the spaces between the iron atoms, you're putting this small carbon atom to stiffen up the metal. So 14 karat gold. I don't know, what benefit do you get by inserting silver into gold? Well, gold's very malleable. Maybe it stiffens it up a little bit. Maybe it just makes it cheaper, right? So you mix in some silver with the gold, and you get an alloy. Interstitial alloy, right? So steel, there we are. So you see the little carbons there, right? So little carbons in the gaps between the irons, right? This helps stiffen up the crystal so it's not so malleable. All right, so which of the following properties would you expect to have, expect to possess metallic properties? Titanium chloride? No, that's an ionic crystal. A mixture of nickel and cobalt, right? So those are two atoms, I guess, about the same size. So you get a substitutional alloy. Tungsten is a metal, so you'd get metallic properties. Germanium's a metal, so you'd get metallic properties. Scandium nitride? No, that's an ionic compound. Classify each of the following statements as true or false, right? So substitutional alloys tend to be more ductile than interstitial alloys. Yeah, that's true. The whole point of an interstitial alloys is by putting atoms in the gaps, you stiffen it up, all right? So brass, you're not making it stiffer, I don't think, by putting the zincs in there. But you are with steel, right? So you put the carbons in between the irons, it stiffens it up. So interstitial alloy, substitutional alloy. Interstitial alloys tend to form between metals of interstitial alloys tend to form between elements of similar ionic size. No, you need a much smaller atom to fit in the gap between the irons, right? So this is why, you need a smaller atom to fit in this gap. So false. Non-metallic elements are never found in alloys. No. Carbon's a non-metallic alloy. I guess you're not getting much of a reaction between the carbon and the iron. So, the carbon and the iron retain their properties, but you get a mixture. Indicate the type of crystal, molecular, ionic, molecular, metallic, ionic, or covalent. So each of the following upon solidification would be, well, calcium carbide, that's an ionic crystal. Platinum by itself, that'd be a metallic crystal. Zirconium 4 oxide would be a ionic crystal. Table sugar, you'd have sugars at the lattice points, right? So held together by hydrogen bonds. So molecular crystal, right? Van der Waals forces holding it together. And benzene, right? You'd have benzenes at the lattice points held together by London forces. So molecular crystal. So ions at the lattice point, well, I guess core electrons and metal atoms at the core electrons, and nuclei at the lattice points for metallic crystals, and molecules at the lattice points with molecular crystals. I guess we didn't have a, molecular crystal. We don't have a example of a covalent crystal here.